we start second day of our conference, and plenary speaker of this day is Marc Georg from Faculty of Chemistry Technology, University in Munich, Germany.
Okay, Igor, thank you very much. It's nice that you're doing this event again. As I said before, it would maybe be nice to do it on site in Aveiro. I enjoyed this place very much. So maybe next year we can do it in person again. So yeah, so it's just now a small group of people. So please, we can do this very easygoing, you know, like in a seminar. You can ask questions, just unmute yourself and freely, you know, pop in, ask questions. I'm not sure how many of you do electron microscopy, and I'm not sure how interested you are in electron microscopy, but my aim is to get you interested a bit. And the most important thing is that I want to, again, highlight that it's important to do electron microscopy, not just in vacuum, but to do in-situ electron microscopy. So as most of you know, that these modern instruments, they are extremely potent. We have nice user interfaces. It's basically easy to shoot nice pictures where you see atomic resolution. Here there's some silicon dumbbells seen, so you can, the resolution is good enough that you see actually the empty space between the atoms. And not only can we look at crystalline materials, we can also really visualize individual atoms with these microscopes. So there are some CR atoms on a carbon support, and you can really see individual atoms. Now this is what microscopes can do, and you can actually even, you know, record EDX spectra and identify the atomic species, and you can record energy loss spectra and get chemical information about oxidation states and all these kinds of things at very high resolution. Now here we have used these images and that are generated by electron microscopy to characterize materials. And in case when materials are used for something, like when we study the properties of materials, like in catalysis, for example, that's the field where I'm working, we have these pictures at all details and resolution and everything. But there are two traps, and one of them is you study all the details very locally at very high magnification. But when you do that, you run the risk that you miss the context. So you know a lot about some small details. So TM is the best tool to know more and more about less and less until you know basically everything about a few atoms, but probably you miss the context in which these atoms should function. And especially when you study something like catalysis, the problem is that these pictures taken in vacuum do not really represent the state of a catalyst when it is in the presence of gas species doing some catalytic reaction at high temperature and so on. Yeah. So the way how we try to get away of this, like, you know, very local context-free imaging of atoms, but to approach more like relevant observation that is meaningful for catalysis, for example, is that we combine in-situ scanning electron microscopy with in-situ transmission electron microscopy. So these two instruments, with some modifications, they can be used to study gas-induced, light-induced, temperature-induced, electrically induced processes. And today, I will mostly speak about in-situ scanning electron microscopy. Yeah? So the topic is really about that. And I start with a very general introduction about the history of environmental scanning electron microscopy. And if you're interested in the history and the development and in general in situ scanning electron microscopy, you should really search for Mr. Gary Danilatos, and he has a nice web page where you can read all of the history of in situ scanning electron microscopy. So what is in situ scanning electron microscopy? So this tool allows you to image materials not only in vacuum. You can set a certain pressure, you can play with temperatures, and you can then look at materials beyond the level of normal scanning electron microscopy, where you often have to code things to make them conductive and so on. So in a scanning electron microscopy, you can look at non-conductive materials, you can look at wet samples. So this picture, for example, shows vegetable oil in water emulsion. So you can really look at wet samples. You can, Daniel has shown all of this and used all of this. So you can also look at, for example, ice crystals. You can look at the formation and growth of ice crystals by using a cooling state. So it's really a nice and versatile approach to microscopy. And basically, the instrument is not very complicated. It's like a normal SEM where you have like the electron source and you accelerate the electrons and you basically form a focused beam that scans across the sample. That's the normal SEM. And the big difference between a normal SEM where everything is in vacuum and also the sample is in vacuum is that in an environmental SEM, you have, after the electron optical column, you have somewhere here, I hope you can see my mouse, in this place, you have a differential pumping aperture. That allows the electrons to still fly in a good vacuum through the optical apparatus, the scanning unit and so on, where the beam is formed. And only before entering the chamber, the electron passes through some differential pumping apertures where the pressure is stepwise increasing. Yeah? So you have then like a long mean-free path for the electrons through the optical column. And once they enter in the chamber, there are some gas molecules around and you can have scattering events. Yeah? And here's the reason why it actually still works. When you look at the good vacuum, you have all the electrons coming, flying through this differential pumping aperture into the chamber, heating the sample. And if there's a good vacuum, most of the electrons are getting focused to a point. Maybe there's sometimes a scattering event with a gas molecule in good vacuum and that gets scattered. Now, if you have more gas molecules around, you get more scattering events. But the good thing and the important thing is, as long as there's still some portion of electrons still getting focused to one point, you still get a signal from this point. Whereas all the scattered electrons, they get scattered randomly. They only give rise to some kind of a background signal. So you get a background signal from the scattered electrons, but as long as you have still a few percent of the electrons that are getting focused to still one point, you can still get an image. And that is actually amazing that only 5% of the electrons remain unscattered, you still can record an image. Yeah? If you have too much gas, then there are too many scattering events, and then you don't get an image anymore. What you could do here is you could actually place your sample further up, move it closer to the entrance aperture, and then you could probably still see something. Yeah. So it works as long as a sufficient number of electrons still remains unscattered, then you can still do imaging. So you have to have this differential scanning aperture. And then when you work in gases, you also need to have a different detector. So this is a view in the chamber of a microscope where you have the normal secondary electron detector. That's the Eberhard-Fermi detector. This detector requires high voltages, and it would not work in gaseous environments because he would generate a plasma. So this guy is switched off when you work with gases. You can still use backscattered electrons. And then there is this also, due to Danilato's developments, there's this gaseous secondary electron detector pictured here. And that is actually a very simple thing. It's just a metallic plate on a positive potential. And what happens is that the electrons that hit the surface, they generate secondary electrons. These secondary electrons, they are getting accelerated towards the positive anode here, which is sent to the sensor basically. And on their way, they can hit gas molecules and create secondary ions. And the secondary, this leads to the acceleration of charged electrons that can again ionize and create further secondary electrons. And so you basically get an avalanche, like in a Geiger-Müller counter. So this avalanche effect is like giving a multiplication factor. So one electron that is like created when the primary beam hits the sample can generate many more electrons that are getting accelerated towards this positive plate of metal that is your detector, and you can then get the signal. So depending on the type of gas, you get some different kind of gas amplification factor. But this is cool. So we can use the gas actually to amplify the secondary electron signal. So that's how it works. Now you know how in situ or environmental scanning electron microscope works, and I would like to show you now some applications. So what we have done, we have built a gas feeding system that is here in the back, and we can dose very, very clean gases with gas filters, and everything is built on a UHV level. So we can dose different types of gases directly into the chamber. We can control the chamber pressure and the flow of gas into the chamber. We build a heating stage, and you see here a mass spectrometer, so we can analyze the composition of the gas phase in the chamber. And then we can do experiments. And I will show you a few examples here. We start first with an example that we did at the very beginning, which was a quite dirty experiment, because after this experiment, the whole chamber was contaminated, and my student at that time had to clean the microscope for several weeks until we got rid of all the zinc oxides that we deposited. So what we wanted to do is we wanted to grow by a vapor, liquid, solid, VLS method. We wanted to grow nanostructures. A colleague of mine, he was growing zinc sulfide nanowires in his vapor, liquid, solid growth process. And he wanted to look how this vapor, liquid, solid growth actually happens in real time. And so what we did is we had a mixture of two precursors. One was the cadmium sulfate and the other was zinc sulfate, and we mixed these two together. And we had a few silver nanoparticles also added here to this mixture. And then once we heated it up, the silver cadmium sulfate and the zinc sulfate, they were vaporizing, but there were the silver particles, and on the silver particles, the vapor condensed, and then you have this vapor condensation, liquid solid growth of the nanowires, and that's what we were observing. So in these videos, you can see these bright guys. These are the silver particles. There's a lot of vapor because we heat up, and the vapor condenses on these nanoparticles of silver, and you form these rods, which in the end turned out to be zinc sulfate nanorods. And so by watching this growth, we could then, abstract some information about the relation between the particle size and the growth speed. We could also investigate reasons for the branching behavior. So you see in this video, you see that there's initially one rod forming, but at one point suddenly you see that there are some branches forming. And so that by looking at things as they're happening, so for example, you can see that this silver particle on the way up loses some of the silver on the neck of the rod, and this silver then aggregates to the surface and forms smaller nanoparticles here, and these nanoparticles then give rise to the formation of these branches. So we could look at it, we could observe it, but as I said before, after the experiment, the chamber was completely dirty. Another example of where we can learn by direct viewing is a thin film dewetting process. So there's lots of, we do lots of coating processes in technology where we have a defined thin film of a material on a support. And then depending on temperature and treatment, it can happen that this thin film that you grow in a controlled manner gets destroyed or dewets. And this dewetting behavior we studied in a collaboration with Christina Schreif from the Max Planck Institute in Düsseldorf. You can see here that we can in real time observe how the dewetting happens. So we have here a thin film that is dewetting as we heat it from below. And as you watch these things, you can then abstract information. You can see how does the dewetting front propagate depending on the facet that is forming, for example, during the dewetting process. Or you can analyze, as in this, sorry, there's the barn disturbing the video. But anyhow, so you can abstract data because you see it as it happens. And in this case, we analyze the curvature of the growth fronts, dewetting fronts, and the effect of the curvature of these fronts on the speed of dewetting. Yeah? So it's nice when you see something as it happens, and you can analyze in further detail. Another example where we used in situ scanning electron microscopy is when we studied the corrosion of stainless steel interconnects in fuel cells. So fuel cells are operated under very harsh conditions. And one of the problems is that these interconnects that connect the stack of the fuel cells, they are also exposed to these corroding conditions. And the corrosion behavior is crucial for the degradation of the fuel cell. Yeah. And so we looked at this special stainless steel under high temperature oxidizing conditions. So here's a scheme of a fuel cell stack where you have always this anode electrolyte and the cathode, and this stack of this anode electrolyte cathode is held together by these stainless steel interconnects. And we looked at the corrosion behavior of these interconnects. And so we heated up, as you can see here, to 800, more than 800 degrees C in an oxidizing atmosphere, and we observed how the material changes. And this is the time here. You see, we did a very long-term experiment, so 600 minutes, so there's 10 hours and even longer. And we saw how this stainless steel corroded in the influence of oxygen at high temperature. And here it was very interesting because this stainless steel was specially made in the purpose to prevent corrosion. So you have here a cross section through this interconnect, and you can see that there is, for example, cerium, cobalt, chromium, iron, manganese, all these elements, and there's also oxygen and titanium and so on. And there, what I find fascinating is that there's on the surface, there's a diffusion barrier, which is a cerium here. You can see that in the map, that is about here. And on top of it, there's a cobalt. There's a bit of oxygen. That is before the corrosion. And after corrosion, we did again a map. I mean, you saw the video before, there's a lot of things happening. The funny thing is that the cerium diffusion barrier is still intact. But when you compare, for example, the chromium was completely below the diffusion barrier. But after oxidation, when you look at this map, you see that the chromium has completely diffused through the cerium diffusion barrier. Yeah, oxygen, of course, also went up here. Cobalt is still up there, but it is very interesting to see how the material has oxidized. There's preferential diffusion of some elements that are more prone to get oxidized compared to others. So it's very, very interesting to see how the different elements here diffuse through the diffusion barrier, like the chromium. And the manganese also, it is below the diffusion barrier, but after the experiment, here's the diffusion barrier, the cerium, you see that the manganese has also gone up to get oxidized. Yeah? So, and we can see this in real time, and afterwards analyze a cross-section and see where the elements have gone. We also did some experiments. This is just very preliminary. We didn't really follow up with that, but we also built liquid cells that can be put into the scanning electron microscope. Here we used a very thin graphene membrane, basically. Then we could have beneath the graphene membrane, we could have an electrolyte, and we could look through the graphene membrane into the liquid, basically. Then apply potential as a potentiostat and deposit some material on the bottom side of this graphene membrane. Yeah? But this is something that I would like to continue. We just stopped at that point when I left the Friedrichshafen Institute. And the next thing that we started is like oxidation processes. And I'm just showing here, like for the fuel cell, but in this case, it's a simple metals, like in this case of copper. We studied the corrosion behavior of copper. And the interest, of course, was not just only study the corrosion behavior, but we wanted to study the redox behavior and finally catalysis. I just show you this video to impress you a bit by the beauty of following and being able to follow oxidation processes. So when we apply here some temperature and introduce tiny amounts of oxygen, we can observe how the copper forms a copper oxide. And as this video goes, you can see that there is like it looks like there's a wave in front of the oxidation front. You see the oxide that has a different structure, of course, and you see the oxidation dynamics, and they can be different for different grains. So in the next video, you see there's a polycrystalline copper foil. Some grains only surface reconstruct, and on other grains, in the same condition, you already form the copper oxide. And when we observe the oxidation process, here we see this oxide growing. When we look at some details like here, we see macroscopically the growth of the oxide, and we know from in-situ TM that it's like a step flow growth of atomic layers. And so we can in the SEM see the macroscopic version of what happens on the atomic scale. So I find it quite fascinating that in a simple tool, you can directly observe oxidation processes. And of course, we were more interested in real chemistry. So we also studied redox processes. So we can, of course, simultaneously introduce different gases together. And this video shows what happens when you have hydrogen and oxygen mixed together and they both react with the copper. The poor copper gets oxidized by the oxygen, forming copper oxide islands, as in the videos before. And then hydrogen can reduce the oxide islands back to the metallic copper. And in all this dynamic redox process, of course, at one point you form also water from hydrogen and oxygen. And we see these dynamics of the surface And we can observe these dynamics and correlate this with the amount of water that is forming on this surface. So we can correlate a bit catalytic activity with surface redox dynamics. And you can look at these islands that are getting reduced and disappear with time because of the action of hydrogen. And we see that some of the islands are growing because of the action of the oxygen. And yeah, so we mapped the whole regime of like temperature and ratio of hydrogen to oxygen. And you see that this dynamic of the surface very sensitively depends on the amount of hydrogen and oxygen, of course, and then temperature regime. And we also found regimes where it's like I tried to indicate this here with these colored waves here, so that it's not so chaotic, but they're like waves propagating where the surface state changes from a stepped surface to like a flat surface, and then there is oxide islands and they disappear, and then you have again the step and then the flat and the oxide. So there's like a concerted dynamics on the surface. So anyhow, so this is fantastic. So we can directly observe the surface of a metal under different gaseous environments, and we then grouped up with Point Electronics. It's a company that builds, rebuilds, refurbishes SEMs, but they also build detectors. And so they built for us a detector that allows us to do 3D imaging, even on very hot surfaces. So we are able to study surface dynamics at temperatures of up to more than 1,000 degrees. And with this special detector, we can record 3D topological images of dynamic surfaces. Then once we did all these surface reactions, we also started to look at the NO2 hydrogenation on platinum. This is a quite beautiful experiment, as I think. So we had a polycrystalline platinum surface. And what we're looking at here is really the reaction of NO2 with hydrogen that happens on the surface. It's a very like surface localized reaction. And as I play the video, we start with NO2 in the chamber, and then we slowly add hydrogen to induce this NO2 hydrogenation reaction. And depending on what is on the surface of the platinum, we see changes in the emission of secondary electrons. And we're very sensitive to surface coverages. When the surface is covered, the work function can change, and this changes the amount of secondary electrons that comes out. And we see this very sensitive. So as we add hydrogen into the NO2 flow at one point, we see that we can initiate the surface reaction. And then we immediately see that there's chemical waves propagating across the surface. We see that different grains show different catalytic activity, and we can correlate grain orientations, catalytic activity. We see how waves can enter non-reactive regimes. We can see how grains can couple across grain boundaries by spillover. So we learn quite a lot by just looking at these dynamics. And the important thing here is, first of all, the SEM is actually a relatively simple instrument, but you see it's very, very, very surface sensitive. And these dynamics that you're seeing here, they can only be seen while they are happening. So if you look at this surface not in the reactive regime, you have no idea of how beautiful these reaction patterns can be. So these are things that you can only see when you look at them as they are happening, so by in-situ electron microscopy. So we realized that the SEM is actually as surface sensitive as a photoemission electron microscope, and this allowed us to publish this in a quite high journal. And yeah, so now you have seen a few applications where the SEM reveals dynamics that are happening when the material is exposed to temperature and a reactive environment. That's the starting set. And of course, there is another beautiful thing about these scanning electron microscopes. Compared to a TEM, compared to a transmission electron microscope, where you're really very confined with space, you don't have much space inside the TEM. You have to insert your sample hole, and there is like nearly no space. The SEM has a huge chamber, a relatively huge chamber. So it is possible to add additional instruments into that microscope, and then you get like a correlative approach. So you can have different combinations of tools that look at the same place at the same time. And so one thing that we have installed inside the SEM is an atomic force microscope from the company Nanovision. So there's a little mic, that's AFM, that is using self-sensing tips. And you can put that into the chamber. So you have the electron beam observing what is on the surface, and then you have the FM tip. And the beautiful thing is you can then do correlative probe imaging. So you can have the electron beam and the AFM tip at the same time. And you, instead of scanning the beam, you just scan the sample and record the signal from your AFM and the secondary electron signal at the same time. And this brings some advantages. First of all, it is fantastic because with the SCM, you can first search for a region of interest, and then you move the AFM tip to that place. You know, if you do AFM, you know that it's sometimes difficult to search with an AFM that has a very limited scanning regime. It's difficult to search for a region of interest. But when you have the SCM, you can scan your sample, localize a region of interest. In this case, for example, we looked at graphene flakes on copper, and we use them. You know, that's the next thing. You can have different ascending tips. So we use Kelvin probe microscopy on this graphene copper thing to see how the work function differs from copper and graphene covered copper. So this is fantastic. You have the SCM, you find your graphene flake, then you move the Kelvin probe AFM to that place, and you take a Kelvin probe force microscopy image. Yeah? So that is, I find this very, very fascinating. And then, yeah, this is very interesting, this combination, because you can study work functions and as I mentioned before, when I showed you these spirals of this NO2 hydrogenation, we are sensitive to work function, but we cannot quantify them in the SCM. But now I have the Kelvin probe microscope, and I can measure different work functions, surface potentials, and then correlate it a bit maybe with the secondary electron signal that I record. So the two methods, they really profit from each other. And of course, this the AFM, as I've mentioned before, you can use different types of tips that deliver different types of information. So we are also able to do magnetic force microscopy. And then you can study in an SCM very nicely magnetic fingerprints and features of samples. So here, this is a topological image of a sample. We can take the secondary electron image at the same time, and we take a topological images with the atomic force microscope. But we can also look at the magnetic force signal, and then we see the magnetic structures in that film. So I think that adds really a new additional kind of information to the SCM. And what we have started now to build in collaboration with the company Nanovision is a heating table. So we can do also temperature dependent measurements in the SCM with the AFM, with the different tips. And because we have an environmental SCM, we can of course introduce gases at the same time. So we can induce changes of materials and then use the combination of AFM, SCM, and all the different capabilities that the AFM brings in all together at the same time. So that's one thing. Another thing we recently started to try out is to put a calorimeter into the SCM. And we worked here together with Mettler Toledo. They built flash DSD, so flash scanning differential calorimeters, which is basically put the heart of such a flash differential scanning calorimeter and install that inside the chamber of the SCM. And now we can measure heat flows very precisely, and we can study phase changes, for example, and at the same time watch. Yeah, so we have here an adecticum of gold to silicon that has different transformations as a function of temperatures at different phases that come up. And in the past, people did these experiments in a separated way. So you had the imaging in one instrument and you did calorimetry in the other instrument. But we can put both together and we can heat up, and during heating, we can see there's some endothermal peaks until it melts. And then we can cool down, we can follow all this in real time. So as we heat up, this is this transition. At one point, there is endothermal transition where the phase changes. That happens now. Then there comes the second endothermal peak where it melts. And then when we cool down, we see how the structure freezes again. And that is a new combination that yeah, it's quite powerful. And again, the two correlative methods, they profit from each other. So we have, for example, seen changes in phases that are not registered as a heat change, a heat flow or calorimetric data, but we also have seen some calorimetric information that cannot be detected by the SCM. So they really, the two instruments together, they reveal more about the things that are happening than one of them could ever do. And then just to show you another thing that we installed inside the microscopy, that I find quite exciting. That is based on the work of Ralf Spolenak's group with Colin Reiser. They did electrohydrodynamic redox 3D printing. So basically they have a little metallic wire in an electrolyte. They apply voltage and they make metal ions, and that are then through a little opening, yes, like sprayed to the opposite side, so to the cathode. So you have this positively charged ions that are in the electrolyte, and you spray them onto your surface. And in this way, when you have a little needle-like opening, you can print very tiny structures. And the idea was to do this 3D printing inside the SCM. So we could use the electron beam to image what is spray printed here from this by this electrohydrodynamics redox 3D printing. And we just started this, but as I mentioned before, we can change the atmosphere, we can heat, so we could do this redox 3D printing in an atmosphere of oxygen, for example, then directly print an oxide, or we could do that in a reducing atmosphere, make sure that we print just the metal. So this is the setup. So this is the SCM, optical column that ends up here, and the electron beam comes out here in the bottom. Then we have the piezo stage to move the sample underneath the nozzle from which we print, and it works. So you see here the nozzle that actually sprays, and we grow pillars. We move the sample, grow the next pillar, move the sample, and grow the next pillar. Just play this video again. But this is basically the starting process of like 3D printing fine structures inside the SCM. And as I mentioned, we can do that under controlled conditions. So we can, control the temperature of the substrate, and we can control the environment in which this printing process happens. Yeah. Okay, so and now, how much time do I have? Yeah, 21 minutes nearly. I would like to show some new data that we have on graphene growth. So we were able to use the SCM to study graphene, and as you know, graphene is still a very hot material. Graphene forms by the decomposition of a hydrocarbon source on a hot metal substrate. We use nickel, copper, and platinum, but you can also use some other metals that work for chemical vapor deposition of graphene. And although the graphene is like only an atomic layer thick, we can actually see it forming on the surface. So this video here shows the growth of graphene islands on the copper substrate that is here heated to nearly 1,000. Yeah, it's 1,000, about 1,000 degrees here. And you see the growth of these copper islands some of them grow at grain boundaries and so on. So we study all these details of the graphene growth on copper. We can see how the individual flakes grow as a function of time. We can learn a lot about the influence between neighboring graphene islands that consume carbon species. At the beginning, there is no competition for carbon species because the islands are far away from each other and they're all eating carbon. But as soon as they get close together, you see that the growth is not working so nicely anymore. So we could correlate the growth speed as a function of the environment, competing other events of graphene carbon species capturing. And then we also, that is something quite interesting, we observed what is happening during cooling. So when you finish growth and you cool down the substrate, when you do that in a chamber that is not extremely oxygen free, so not in a UHV chamber, but you have some partial pressure of oxygen around, then during cooling, the copper can get oxidized, and when the copper gets oxidized, it just forms a very thin layer of surface oxide, but this thin layer of surface oxide gives rise to this, you see the steps that are forming here underneath the graphene. This is because of this effect of oxygen that is still in the chamber. So when you cool down, you get all this step formation. And that is also nice because if you don't see when this happens, you don't really know when and why it happens. But we compare graphene grown in literature, you see that often the graphene has grown on some kind of stepped surface, but in fact, it was not growing on a stepped surface. The stepped surface formed during cooling. So this is from literature. You see people have observed graphene on stepped surface, but this stepping actually happens during cooling. And there are lots of papers that describe how graphene grows on these steps, but in fact, it grows on a flat copper, and during cooling, this stepping happens. And this you can only see if you watch it while it happens. Anyhow, so copper was a bit complicated with issues with sublimation and oxidation and so on. So we did a lot of graphene growth on platinum, which works very nicely. So we first anneal the platinum, and this alone is beautiful. So we do hydrogen, high temperature annealing. We see how the grains like grow, some other grains disappear, and as the surface cleans up. And when we do this very nicely, we get very large single crystalline grains. And we can then look into one grain, and then we introduce ethylene and hydrogen together. And then we form like first a monolayer of graphene. That is the first gray level. You see all these different islands of graphene growth events. They form a complete film by coalescence. Yeah, and then at some places indicated here by the arrows, you see that there's a second level of darker gray in the picture. That's a second layer of graphene, and in other places you see actually multi-layers of graphene that we can still distinguish from changing contrast. So we have removed that film. We did Raman, TM, and everything. We know it's really graphene, single layer graphene here, bilayer graphene here, and multi-layer graphene there. And SCM is fantastic in terms of its surface sensitivity, as I mentioned before, also in these beautiful NO2 hydrogenation reactions with these spirals and reaction fronts, where we see adsorbed species reacting and reacting off. And here we have the graphene, atomically thin layers that we can see in an SCM image, and we can actually count atomic layers. So we have atomic layer sensitivity, so we can count atomic layers in coverage from like relatively bright to until so dark that we cannot distinguish anymore, but we can count up to like 10 or 11 gray values, and so we can count 10 to 11 atomic layers in the SCM. And yes, so as I mentioned before, we did Raman, and we characterized it with TM, and the graphene that we have been growing in that instrument is actually quite nice. Now there's an advantage of doing things in situ. So you have actually the full control of all experimental parameters. So we control the heating temperature of our substrate. We control the gas phase, so we can observe growth. We see here nucleation events on different grains. We observe this, and then we can say, okay, let's stop the growth. We now etch everything. This is all in real time, so you can etch the graphene. Then you can change the ratio of hydrogen to ethylene, and then you can get conditions where you don't have so many nucleation events, just like few nucleation events, like in this case. This real-time control over growth, like here we increase the hydrocarbon, then we get many more islands, then we etch again. This ability allows us to really study graphene growth in a lot of details. If you only look at the sample after growth, it's a bit difficult because you have to run many experiments in series, but here we can do it in real time. And here's, for example, the effect of the surface structure of the polycrystalline platinum. So you have different grains, and this grain is very active, and even there's spillover of graphene to the other grains. And these grains are inactive. They only start to grow graphene when we increase the hydrocarbon pressure. See, there's graphene growing here, and there's retracting a bit. And here there's only nucleation when we increase the hydrocarbon partial pressure. So we can map the activity of a surface for graphene growth as a function of the surface or the grain orientation. And when you do this for many grains, you get like a statistics, and you can analyze that and learn a lot about graphene growth. So in the last 5 minutes or so, I want to show something that is just really very recent. We have not published that yet. And it's about the controlled formation of twisted layer graphene. So we do some kind of like folding, cutting, like this paper, but in this case with graphene. And I don't know if you're probably not in the field, but people have found that when you put graphene and you put another layer of graphene, you get bilayer graphene, or like just the stacked 2D materials, then it very sensitively depends on how you stack these 2D materials on top of each other. You can achieve different electronic properties. And so is this animated? Yeah, so here's what happens when you put two hexagonal layers of, in this case, graphene, on top of each other, and you just change the twisting angle. You see that when they're nicely arranged, you just see the hexagonal pattern, but as soon as you twist them, you form this moire structure. So these are your periodic geometric features, basically, that they are forming here, that change as you change the twist angle. Now, it's not only a geometric feature, it's really influencing the van der Waals coupling between the two layers. And depending on the twist angle, you can really get very, very interesting and exciting properties. So people, this is another animation, just changing the twist angle. You see how the moire pattern changes? And people have studied that you can, in twisted monolayer or bilayer graphene, you can get very, very exciting properties. You can get superconductivity, and you can get special spin states and so on. And it's so important that it even coined the name twistronics. So it's really a new field that is just made up by people who try to control the twisting angle between layers of 2D material. So there's superconductivity, magic angle graphene superlattices, and electric field controls, solid tone motions, a lot of electronic states that you can basically tune by tuning the twist angle. So yeah, it's quite a hype, and it's good to publish in high-level papers, twistronics. Yeah. Anyhow, so how do you do that? So people have studied that, but it's not easy. You cannot just fold graphene because it's a monolayer of a sheet. But people have tried to transfer a little piece of graphene and put it onto the other, and then use a local probe to measure if they really induce some special electronic states. And this is all happening on very, very small scale. Can you imagine? They take a tip of a scanning tunneling microscope, and then they try to fold in some way the graphene. So this is like a sheet of graphene. Basically, they fold it over the same thing, and then they do measurements, and they can also unfold it again. So this is very precise control. Here is an atomically resolved picture of this folded layer. You see, when you fold it, you have on one side, of course, you have on one side this bent part here. That's basically this thing here, and then due to the van der Waals interaction, the two layers they collapse here on that side. So you have here very close together the two layers, and then here the fold, and you can image all this. Now, because we can control the graphene, as I showed before, quite nicely, we were actually realizing that we can control a bit the folding, and we can induce folding in specific directions. And I'll show you this video here. You see here is there is no graphene yet. The gray level is graphene, and it's here on the platinum surface that is obviously stepped. You see these steps here? So it's a stepped surface on which you have a conformal layer of graphene. Now that's already graphene, and what we do now is we have a very high temperature, and we can reconstruct that stepped grain. So you have you start with a stepped grain. Let me just quickly do that here. This paper. So you have a stepped grain, and then there's graphene on top. And what we do then is we recrystallize the grain such that it gets flat. And this is what happens in this video. So this is we heat further and we recrystallize that grain. So there's another grain orientation propagating into that grain. So basically, it's a surface reconstruction. This grain of platinum that was stepped disappears, and the flat grain moves underneath. Now there was graphene already here, but as the substrate underneath suddenly gets flat, that's happening here, the conformally coated zigzag graphene has too much space, and you form these guys here, which are actually wrinkles. Yeah? So we have analyzed the surface structure of this grain and that grain. That grain, we saw that this grain here is stepped. It has a graphene film, but when you have this stepped graphene film and you suddenly make the surface flat, then the graphene is just loose. And what we actually form is wrinkles. And the wrinkles, they collapse and fold over. When the wrinkles fold over, you have not only a monolayer, but you have three layers. You have the bottom layer folds backwards and back up, so to the left and back to the right. So you have in the middle, you have three layers that gives this dark contrast. So we realize that's here showing again in the sketch way, you have a flat grain that expands underneath the stepped grain. And as the flat grain expands, you have too much graphene material and you form a wrinkle. That is happening while in this process, when the flat grain grows underneath or changes the surface of the stepped grain. Yeah? So you form a wrinkle. And this wrinkle is not stable. Yeah, it falls to one side or the other, like shown here. So you get a tri-layer basically. This tri-layer is darker in contrast. I told you we are sensitive to the atomic layers, and we can see tri-layers that are basically 3 levels darker than the single layer. Now, as we control the growth process, we can actually etch, that is funny, we can etch this highly curved graphene fold with hydrogen. So when you etch this highly folded, graphene can easily be etched when it's like geometrically very strongly bent. Yeah? So we can etch open this with hydrogen, and we make 2 new growth fronts. And these guys then continue growing, and you see that the surface first layer is some gray level, the second layer is this layer, the third layer is that layer. That's the model, but you can see that, I mean, maybe I should zoom in. You can see that in the image here slightly. It's not very obvious, but I'll show you later. Maybe you can see it here. It's different gray level. Anyhow, so we did some DFT calculation, we did STM measurements, so we can see that the wrinkles really fall to a side. We form this structure. We can etch this structure. DFT confirms that here is the etching happening. You make 2 new growth fronts. When you cut open that folded wrinkle, and then you can regrow. And here's the higher resolution. So when this wrinkle is folded and you etch at the bending side, you etch it open here. Then you get a top side and a bottom side that can regrow. And you see here the new growth fronts that are forming with 2 different gray levels. So that's the first layer of graphene, that's the back-folded bottom layer, that's the back-folded upper layer, and they grow again. Yeah? And so this is the video again. And you can see maybe here the different gray levels from this bottom layer and the top layer of the opened wrinkle. Yeah? And the funny thing now happens that depending on how you fold, depending on how the wrinkle is oriented with respect to the orientation of the graphene, yeah, you get a top side and the bottom side that as shown here. So this is like, let's say these are zigzag edges of the graphene, and when you fold, you get an upper orientation and a lower orientation. That happens due to the folding, and the folding axis is not coinciding with the zigzag direction of the graphene. Then you get a twist angle between the top backwards folded layer and the bottom layer. And this twist angle we can basically tune by growing graphene on differently stepped surfaces. Yeah? And I hope you're still with me. The next thing that can happen is when a wrinkle forms, it can fold to one side or to the other side. And sometimes it happens that parts of the wrinkle fold on one side, and then the wrinkle is ripped apart because another part falls to the other side. This is indicated here with a paper model. So the wrinkle, yeah, ripped, and I can destroy this paper. So the wrinkle folds to one side or to the other side, or it rips off, and part of the wrinkle from one side and the other falls to the other side. And then you get such a structure here. These are these structures that are here at the tearing edge of a wrinkle. Yeah. And now the funny thing happens, we see these tearing edges in the experiment. And at this, when you regrow at these growth fronts, these are also growth fronts where the wrinkle rips off, these are also growth fronts. When it lies on the surface, you form growth fronts here from the bottom and top by cutting open the folding edge. These are also growth fronts, and you get a spiral growth at these sites. So we start to form graphene spirals, and these are the images. So we have a fold, that fold falls to the left or to the right, and in the center where the fold happens, you get graphene spirals. Now each side has a different Burgers vector, so you have 2 spirals that are growing twisted layer graphene. And in the end, you get this twisted layer graphene of twisted layers stacked up together. And yeah, so we can on a large scale, this is a video that shows the real world happening of such a graphene spiral. Here is a single wrinkle with the front and at the top end, we get this spiral graphene growth. And as I mentioned before, it is possible to control the wrinkle orientation on the graphene. And by this, we are able to control the twist angle between the layers. And by growing graphene spirals, we can have large area, stacked graphene layers with a defined twist angle. Yeah? And so here's the experiment, here's the growth simulation. So there was a wrinkle with a front and the bottom end. So each wrinkle has a beginning and an end, and it forms a spiral also from there. And then my former PhD student and postdoc and now Professor Jun Wang, he analyzed all little tiny features of wrinkles, and he found many different fantastic configurations of wrinkles. If, for example, if a wrinkle is not straight but folded, you can have very complex combinations. And this goes now too far. I have finished my hour, and I just want to highlight. So first of all, I want to thank Jun for his fantastic work. And secondly, I want to highlight that the SEM allows you to study processes, even as crazy as graphene that grows at 1000 degrees and gives you an atomic layer only. But you can observe it, you can watch it, and you can study it, and you can derive atomistic details about the process by observing as it happens. Even so, the microscope itself does not have atomic resolution. I think that's it. Thank you very much. And if you have questions, please let me know.
Thank you very much, Marc, for very interesting presentation and interesting result and interesting technique for interesting materials. Okay, now we are open.
I destroyed my letter, but I hope you could see me. I don't know if you could see me while I was talking, but yeah.
Okay, I think Alva, what is you want to ask
yes,
something? Okay,
yeah.
okay.
Yeah, I thank you very much for your very interesting presentation. So
Thank
in
you.
fact, I use also SEM in my PhD study. I use Oxford machine. So we use the SEM with the polymer, and we got it hard to get a very nice image because the polymer will maybe affected by electrons. We avoid to use the coating because some people using coating, for example, gold coating, but we were focusing on the very small parts, and maybe the coating will hide very important information or the polymer particles or polymer surface. So we used the very low pressure, low voltage, around 1 kV. But yeah, so it's also that's not very good option for with the low voltage, because also we cannot get like a very clear SEM image with the low voltage below 1 kV. So what do you can suggest for us, for such as these like issue or challenges? Yeah.
So I understand your approach. When you have materials that are beam sensitive, that's of course a difficult thing. And when you have materials that are non-conductive, then you get all this charging. You can, and you did this correctly, you can change a bit with the acceleration voltage because the secondary electron yield, so how many electrons come out per each electron coming in, changes as a function of the voltage. So you can maybe get a charge neutral regime. But actually, if you operate in an environmental SEM, when you have a gas phase, the gas phase discharges the charge that builds up. So you can look at non-conductive samples like liquids or isolated ceramics. So if you would use an environmental SEM and play with the ideal pressure of gas and also the type of gas, you could image your materials nicely.
Okay, yes, okay.
So use the gases secondary.
We normally use, I think it's vacuum with the nitrogen gas. Yeah.
Nitrogen works as an imaging gas, but some people use water, and we use different types. We play with different gases have different imaging properties. So argon works fantastic, but you can also use hydrocarbons. It depends on your material also, a bit on your application and what you want to study. But there's a lot of space to try out.
Yes, yes. Okay. Okay. Yeah. Thank you very much. Thank you.
You're welcome. You're welcome.
There you go.
Any more questions? If no, I have several questions about IFMs.
Yes.
Logically.
I would be happy if we could collaborate in future, because I will
Okay.
try to continue.
Very simple question. What is cantilever do you use? Standard cantilever, IFM cantilever?
So it is self-sensing tips, and for different, you know, piezo force microscopy.
As I understand, it must be like angle, or it's vertical. It is not. It's,
no, so we come from the side and we use the tip, and it's a self-sensing tip with the.
Use standard cantilever.
Yeah.
Okay, and what is the resolution of
Yeah, so I would actually, I mean, it depends on the tip's shape and
yes,
so on.
Yes,
so
of course, of course.
Yeah, it was not the optimum.
No, this is question is you in IFM reach same resolution, or it's what is relation between?
No, the SCM resolution in our SCM goes down like to 2-3 nanometers, and with the AFM we were above that. But we are working with Nanovision, and they are having a collaborator to build better chips. And actually, I have an idea to you know, to get away from self-sensing chips, but use the electron beam, like the laser deflecting. You know, normally you have the laser beam deflecting, and I want to use the electron beam and do electron backscattering.
But now you use optic. Now you use laser. Yes.
No. Now it's self-sensing chips, self-sensing without laser. So the tips have basically on the surface, like, I don't know the English name, but the self-sense deflection, without the laser.
Without?
Yes, without laser, self-sensing tips. So yeah, so it's not, that's why the resolution is not.
Okay, I understand you construct in our atomic force microscopy scheme. Okay, and okay, thank you about this. And again about atomic force microscopy, you show Kelvin probe.
Yes.
Do you find any effect electron beam on your face after, and if you see a Kelvin probe, it's have some.
So the Kelvin probe we can do simultaneous SEM and Kelvin probe microscopy.
No,
but
after question, do you have any effect?
No, only if
electron beam during your SEM imaging on the
it can happen
on potential of your face. I think it must be some effect.
So we didn't do it simultaneously here. We did the first image and then the Kelvin probe microscopy method.
Yes, it's absolutely.
But in the electron microscope, sometimes if you're not working in clean environments, you can, with the electron beam, deposit a layer of contamination, and that would, of course, destroy your Kelvin probe microscope signal, because everything has then a carbon level of coating. But I wanted to use this Kelvin probe microscope actually as a sensor. So we have chemical reactions that propagate on the surface, and they change the work function. And I was thinking I'd just place the Kelvin probe tip at a local point, and I measure passing waves where the surface work function changes. So we just really started with these whole experiments, and I'm really at the beginning. So in the future there will be better tips, better self-sensing things, and Nanovision has now new lock-in amplifier, and I hope that I get a new instrument by the end of this year. And I would be very happy to collaborate with you, because you're an AFM expert.
No, you can collaborate with any IFM company who construct. Okay, you collaborate with company, yes.
Nanovision, yeah, and they have some people who make
they know how organize Kelvin measurement. But yes, this is interesting, because on your electron microscopy measurement, you don't know what is potential. Yes, it's
exactly.
In this case, this is. But in IFM, this is very easy to obtain.
Yes, exactly. That's why the combination of the two tools
Yes,
is
in
so
this case,
fantastic.
yes, maybe this is interesting. Okay, thank you.
Thank you.
Any more questions? Okay, thank you. Okay, if no question, thank you very much, Mark.
You're welcome. Thank you all for your interest, and see you.
Okay, thank you.